So, welcome to the second lecture on gas dynamics. So, today we will discuss thermodynamics. So, we will revisit first and second laws of thermodynamics. Okay, so whatever you have learned in your previous course. So, this is not going to be an elaborate discussion on thermodynamics and the subject, but just whatever we required for gas dynamics. So, for a closed system, the first law would tell you the heat input is your work done. So, this is heat into the system, this is work done by the system. This is the standard sign convention that we use. For a process going from state 1 to 2, we have the heat input equals work done plus your internal energy or the total energy, okay, in terms of between state 1 to 2. So, this is your total energy. Now, for a unit mass, or as we call as specific mass, we use the notation delta Q, sigma Q plus sigma W plus sigma E, all in small letters, okay, for specific mass. We will keep this notation throughout the course. When I write capital Q, it is for the whole mass, small q is for unit mass. And what is delta E, or what is E? E constitutes U, which is your internal energy, plus V square by 2, which is your kinetic energy, plus some potential energy. Okay. Now, internal energy is something that is due to the molecular rotation, vibration and translations and other things of the fluid particles. This is due to the kinetic energy or the motion of the gas, and this is due to the potential of the gas. So, we will assume this to be 0 for the course at least. Now, for an infinitesimal step process, for a small delta change from state 1 to 2, we write dq delta q equals delta w plus dE. This delta is because q and w are path functions, which essentially means the work done and the heat input depends on the path that goes from state 1 to 2. So, if I have a state 1 and the state 2, the delta q and delta w, so this is path 1 this is path 2. So, your delta Q1 and delta Q2 are not the same. Q1 not equal to delta Q2. Likewise, the work done is also not the same, which essentially means there is a path function, and hence any incremental change is denoted by delta Q and not dq. Okay. So, if the process is stationary, obviously V is 0, so your internal energy is just U. So, your delta Q is delta W plus du. Fine. We also define something called enthalpy, which is U plus PV So, this internal energy and your combination of pressure and volume. So, here V is volume. So, this V is velocity. So, to avoid confusion, I would write this as small v, which is volume of unit mass, and capital V is velocity. So, I will again keep that particular notation. So, whenever there is a confusion between these two notation, I will try to refer that. Okay. So, the enthalpy is defined like this, which essentially means if I differentiate this for a small process, this would be du plus P dV plus V dP which is called Cp and Cv. So, what I am going to do is differentiating this equation, differentiating the first equation, I get dH by dt at constant pressure into dt plus dH by dP at constant temperature into dP du is du by okay. So, this is volume. So, this is volume. Okay. If the process is constant pressure process, obviously the first equation is dH is dt, where we define the coefficient as Cp, which is specific heat capacity as dou H by dou T at constant P, okay, or dH is Cp dt, okay. But remember, this is also a function of temperature. Cp is also a function of temperature. Okay. Likewise, the second equation, if the process is process, my du is dou u by dou T at constant volume into dt. And now I define Cv, which is specific heat capacity at constant volume. So, this is at constant pressure. Okay. So, my du is Cv, again function of temperature, into dt. So, for chemically inert gases, your specific heats are functions of just temperature. It is not going to be functions of other quantities. Okay. So, such gases where Cv function of temperature, Cp function of temperature, such gases are called thermally perfect gas. Okay. So, thermally perfect gas means these equations are valid and specific heats are just a function of temperatures. Okay. Now, if they are also constant, constants, then you have calorifically perfect gas. Okay. So, in this course, we will deal with only calorifically perfect gas. Okay. So, for all the gases that we are going to consider in this course, Cp and Cv are constant. Okay. Okay. Now, we will continue with our laws of thermodynamics. Now, we have defined enthalpy, we have defined our internal energy, and we have defined the first law. We are written the first law as this. Okay. Now we will discuss the second law. So what's the second law? In reversible process, you have, say, from, let's like, so how do you define a reversible process? A reversible process is if you can bring back, if the system and the surroundings can be brought back to the initial state. Okay. So if you do a process from point 1 to 2, state 1 to 2, if you can bring back the system and the surroundings from 2 to 1, then that process is a reversible process. Now for a reversible process, from state 1 to 2, what is noted here is the delta q by t, or delta q by t is or does not depend on the path. So whether I go from this path or I take another path, the delta q by t is going to be just a function of that particular state, okay, that location of the state. So from state 1 to 2, delta q by t is going to be same, which means what? Which means delta q by t is a point function, and point functions are function implies delta q by t is a property of the system or of the process or whatever. This is defined as your entropy. So for a reversible process, this is defined as process. So your ds reversible is dq by t. So for any process, your change in entropy is then ds reversible and ds irreversible. So your irreversible entropy change is essentially due to friction or viscous heating or viscous dissipation, and this is your actual heat addition, which is defined as, which is given as delta q by t. So if I rewrite that equation, So, irreversible entropy. So, irreversible entropy is always going to be happen or always going to be there in any real flows. So, ds irreversible is always greater than 0. Okay. So, which essentially mean that the total entropy change is always greater than ds reversible, or ds always greater than delta q by t. And this is the so called Clausius inequality. Fine. So, this gives you as given in most of the thermodynamic textbooks, the second law gives you the direction in which your delta Q and delta W works. Okay. Remember, delta Q is the heat input into the system, delta W is the work done by the system. So, my first law gives me this equation, my second law gives me this equation for a reversible process. Okay. So, this is from your second law, this is from your first law. Okay. Now, delta W you can write it as PdV, which is your reversible work done, the work done due to change in your volume. And if I restrict my dE to just du, which means it's a stationary process and the potential is assumed 0, I can rewrite the first law as Tds equals Pdv plus du. Okay. We have also defined our enthalpy as this, from which I can substitute for du. I should get Tds as dH minus Vdt, right. So, this is equation 1, equation 2. So, these two equations, from these two equations we can derive few other forms of change in entropy. For example, let us take equation 1. So, your ds is Pdv by T plus du, I can write it as Cv dt by T. And if I assume PV equals RT, so these V's are all volume V's. Okay. If I assume PV equals RT, my ds is R by V dV plus Cv dt by T. So, my delta S, which is S2 minus S1 between 2 points, is R into ln V2 by V1 plus Cv into T2 by T1. So, your change in entropy is this particular. Now, if I take the other equation, TdS, I will take the T the other side, dH is by T, dH is Cp dt by T minus V by T is R by P. So, my delta S is Cp ln T2 by T1 minus R ln P2 by P1. Okay. So, I can also write this so Cp dt by T, R I write it as Cp minus Cv dP by T. So, I take Cp out, dt by T minus dP by plus dP by no minus Cp by P plus Cv into dP by P. So, if I take PV equals RT, I differentiate this P dV plus V dP equals R dt. Now, I divide this equation by PV. So, my dV by V equals R by RT. R by RT would be 1 by T into dt minus V dP by PV. Okay. So, this is V dV equals dt by T minus dP by P, which I substitute here. So, my delta S or ds is rewritten as Cp dV by V plus Cv dP by P. So, my delta S is now defined as Cp ln V2 by V1 plus Cp Cv P2 by P1. So, along with this equation, R ln V2 by V1 plus Cv T2 by T1 and this equation Cp ln T2 by T1 minus R ln P2 by P1. So these are important relations from which we are going to derive further inferences about several processes. Okay. Now, let's look at isentropic process. What are isentropic process? Process with no entropy change. Okay. So we have anyway defined our ds to be ds reversible plus ds irreversible, which is delta q by t plus ds irreversible. If the process is adiabatic, what is adiabatic? Your delta Q is 0. There is no heat transfer. If that is 0, then your entropy change is essentially all irreversible entropy change. So all irreversible entropy change associated with an adiabatic process is the total entropy change of the system, because there is no heat addition to it. Now in addition to this, if I also assume no friction or viscous heating or etc., my irreversible entropy is also 0. So in such cases, you will end up with, so delta Q equals 0 and delta S irreversible equals 0 implies my total entropy is 0. Okay. Or adiabatic reversible process is isentropic process. Okay. If ds is 0 somehow, whether it is adiabatic or irreversible, if ds is 0, then it is a more general way of defining isentropic process. What you should remember here is all adiabatic reversible process are isentropic process, but the converse is not true. Okay. Now let us see what are these in terms of that. So if the process is isentropic, what will happen to these set of equations? Okay, so we are going to discuss isentropic process. where delta S is 0. So, if delta S is 0, so let us take this equation P and V. Let us take the first equation. 0 equals Zp ln V2 by V1 plus Cv, there is an ln here, there is an ln here too, that was missing, ln V2 by V1. Okay, which I can write it as P2 by P1 equals minus V1 by V2 Cv by Cp. Or P2 Cp by Cp by Cv is defined as gamma, which is your ratio of specific heats so your P2 by P1 equals V1 by V2 to the power gamma, or P2 to the power gamma is P1 V1 to the power gamma. Okay. Gamma equals constants. I will write it here. Okay. So you can also write other forms from the other set of equations. You can write P2 by P1 equals T2 by T1 power gamma by gamma minus 1 and V2 by V1 equals T2 by T1 to the power minus 1 by gamma minus 1, which I can rewrite it as rho 2 by rho 1 into T2 by T1 to the power gamma minus 1, 1 by gamma minus 1. Okay. From these the other two equations. So you can arrive at these relations. So for the process from 1 to 2, for isentropic process from 1 to 2, you could get these relations from your first law and second law of thermodynamics, which has been rewritten in this particular form. Okay. So as I told you in the beginning, we are going to extract what is essential for this particular gas course from thermodynamics. Okay. So we are not going to discuss any other issues that is discussed in thermodynamics courses. Okay. Now I can look at, so PV equals PV power gamma is constant for an isentropic process. Okay. Now I can have other processes where this power is not gamma. Such processes are called polytropic process, where gamma, instead of gamma we have Tp to the power n equals constant. So instead of gamma you replace n in all these equations. So if n equals gamma, we know it's isentropic process. If n equals 0, what is this process? I put 0 here. So Pv to the power 0 equals constant. This is a constant pressure process. Okay. Likewise, if my n equals 1, so if my n equals 1, what is this process? It's constant temperature process, which is constant, or T to the power P, Tp to the power gamma minus 1 by gamma equals constant. So if it's a polytropic process, T n minus n to the constant. So if n equals 1, constant. So n equals 1 is a isothermal process. So if n equals infinity, then you will end up with constant volume process. Okay. So n equals gamma is isentropic, n equals 0 is constant pressure process, n equals 1 is constant temperature process, n equals infinity is constant volume process. Okay. So if you look at these processes in the PV diagram, how does it look? So I have P, V. Okay. So I am going to if the process is from point 1 to 2. So first let us draw the easiest one. N equals 0 is constant pressure line. So it is a constant pressure line. So N equals 0, it is a constant pressure line. Constant pressure. Now N equals infinity is constant volume. So it is something like this. n equals infinity constant volume. Now you have n equals 1 and n equals 1.4 or 1.3 or whatever. Okay. So you have this n equals 1 and you have another process n equals gamma. So n equals 1 is a constant temperature process and n equals gamma is your isentropic process. Now you can draw the same thing in TS diagram. So the easiest one is constant temperature, it's a straight line. Constant temperature is n equals 1 and constant entropy is n equals gamma. So you have n equals gamma. Then you have the other two here and here. N equals 0 and n equals infinity. So, so that ends this capsule of the course. What we have learned is the first and second law of thermodynamics and the constitutive relations, from which we have derived this process for isentropic flow, or the equations for isentropic flows, and we will be using these equations in the subsequent classes. Okay. We will have a tutorial on this particular aspect alone, say a couple of questions, and you can expect the assignments based on these questions, whatever we had discussed today.